Anyway, any questions before we get rolling on this thing? Okay, so on Canvas and also on my webpage, I of course notice they tend to be up, they've got typos and such. I apologize for that. I will update them as we go along, but we'll start at chapter 6. Of course, you've got all the previous chapters if you need to look back for some references, which is the chapter on modules. Okay. You've all seen important examples of modules. What is a module? Well, it is, how many of you know what a vector space is? Ding, ding, ding. That is the first big example of module. How many of you know what an abelian group is? That's another big example of module. Modules generalize abelian groups and more generally vector spaces. After all, what is a vector space? Well, we do lots of fancy stuff in linear algebra, but at the end of the day, in fact, when you first learn about vector spaces, when you're an undergraduate, they give you, almost every textbook gives you a list of these 12 freaking things that's just, I mean, it angers up the blood. When really, like, the first half of it just means, okay, this is an abelian group, right? So the vectors form an abelian group, and then it's got this fancy scalar multiplication, right? And where do your scalars come from? Well, it depends on your linear algebra course, and a lot of linear algebra courses, they come out of the reals, right? If you got a good linear algebra course, they might go into the complex numbers, rationals, or Z mod PZ, something like that. But the common denominator here is when you're looking at vector spaces, your scalars, the magic scalar multiplication comes from a field. The natural thing in mathematics is to say, hey, wait a minute, why do we have to just consider scalars to come from a field? And you don't. And that's essentially what a module is at the end of the day. So let me get another caveat. That a bit, then I will cowardly chicken out. Because most of what's done in this department is done over a community frame. And so I will at a couple of places emphasize left modules and right module, or left modules or right modules. But mostly I will be looking at modules that are two-sided. I'll be more specific about that in a moment. What do you suppose I mean by a left module, given the fact that I've said, okay, this should be just an abelian group with scalars coming out of the ring? That's right. The left module means you can multiply the scalars on the left only. And a right module means you can multiply them on the right. Notice when you've got a left module, then any theorem that I give you for left modules, there'll be a corresponding one for right modules. And then people that like non-commutative ring theory talk about bimodules, right? Because you can hit them on the left or the right. And people that do commutative rings like me will just say, let's forget all this crap. Let's say the ring's commutative. Well, let me give you the first formal bit here. So I'm going to start this in terms of left modules, and I'll explain how you generalize this. A left R module is an abelian group. Just like vector spaces. It's an abelian group that has scalar multiplication. That is to say, it's equipped with a function from R dot M into M. And the value of this function, we usually write as R times M. And we think of this as scalar multiplication from the left by an element ring. And it satisfies for all R, S, and R, and A, B, and M, we have the following. Number one, the scalar multiplication must play nicely with the addition. So I want that, I want it to distribute out. And what's good for the goose is good for the gander. I want it to play nicely with respect to the addition in the ring. And finally, I want when I take R times S, that's scalar acting on A. This should be the same as R acting on the element of M that is S A. Okay, so let me make a couple of marks. So this is just what it means to be an R module. It's a freaking abelian group that has a nice scalar multiplication in the ring. Of course, if this were a right module instead of a left module, all my R's and S's would be on the other side, right? Because the scale multiplication is right. And if it's commutative, then I make no distinction between RA and AR. And that's the easiest case. We'll mostly specialize for that. Mark, if the ring R has an identity and then M is a unitary. Or a unitary lepton module. This will be the default assumption. In fact, if I say ring, I will mean ring with identity, unless I tell you otherwise. And if the ring has identity, I will mean that any module over is unitary, unless I tell you otherwise. If is a division ring, it depends on your 85/10, right? Can anybody tell me what the division ring is? Okay, well, maybe I should tell you. A division ring means that any non-zero element of the ring has a multiplicative invariant. So basically what a division ring is it's a field where you've removed the necessity of being commutative. Then M is called a left vector space. So, right, if you go back to this, my definition of module, you will notice that if, for example, R is a field, then this is basically vector space. In fact, it's vector space. And more generally, we'll say that if you have a division ring, then a left vector space is just a module of that division. So here is that EX here. So I encourage you to work this out. I'm going to write this down as just a fact. When you take, this is true for any module, when you take the zero element of R times any element of the module, you get the zero element module. And this is also when you multiply any scalar times zero element module, zero. For all R and R, see if you verify it. It's not too difficult, but I think it's kind of a good exercise to keep sort of warmed up. Okay. Any questions? By the way, for my definition that I gave you on modules, it probably is fairly clear why a module is a generalization of vector space, because the only thing we really changed was the scalar strength and the ring stuff in the field. I did say it's a generalization of the group. How do I think that? Let A is a given thing. Any ability group you like. Any ability group is a module over what ring? It's naturally the module over. See, any ability group. How does it work? Well, suppose, how does the scalar multiplication here work? What is an integer to play? Right, so let's take this first case. Suppose A is a natural number, like 2, 7, so this is just A plus A plus A n times. Where do you suppose if n equals 0, how should we multiplication? It's 0. What happens? Right, this is negative A minus A minus A absolute about A 10 times. Or in other words, just add A to it 17 times versus the sign. This is true for any abelian group. So any abelian group is a Z module. So any module over Z is an abelian group, and conversely. Right? Handful of examples, and I'll talk about the first homework here. This is an abelian group, isn't it? Do I agree with that? Do I agree with this? Abelian group? Right, I mean, that's a calculus thing, we learning calculus, some two things functions, so. And this is a module over. Oh, man. I got the little rip off, some abelian groups got the module in the same. Right, and it's a vector space. Over Q orbitals. So this one actually, it actually has different structures depending on what you do. You consider this to be a Z module, you consider this to be a Q module, you consider this to be an R module. You could, I'm sorry, a Q vector space or a real vector space. You can consider it to be a vector space over any field between Q and Z. I'm sorry, between Q and M. So there's lots of possibilities with this. Three. If R is a ring and I and R is an ideal, or you might even forget that R is commutative, and it's not commutative, and I might get left ideal, then I a left R module. Sure. Because note, if AB is an I and RS and R, well, notice that by definition, any left ideal is an abelian group, so you got that covered, right? And notice that one because I is actually a subset of the ring, and that's the way multiplication works. 2, R plus SA is RA plus SA, and 3, RSA is RSA, because multiplication of the ring is associated. So any ideal is an R module, where R is the parent ring. Notice, let me point out that this is not an if and only if. right? So you might say, well, does that really cover modules? So you might think modules as generalizations of ideals as well. Do all R modules have to be an ideal ring? And the answer is no. For example, look at Z. That's the easiest example to think of. Z. Any abelian group is a Z module, right? Q is a Z module, but Q is certainly not an ideal in Z, right? Z mod 2Z is a Z module because it's an abelian group, but that's even got a different characteristic. It's not something. Z direct sum Z, that is a Z module, but it's not. So the world of modules is far richer than just ideals. See what other cool things can I throw in? Yeah, so this one, whatever number I'm up to, 4. If R inside T are rings, then T is an R module. And if they're not commutative rings, you can throw in flat. Right? Because R is a subset of T, and basically what you need for modules are these multiplication things that all hold in T because it's a ring. Right? Notice that when you multiply something in R, comes something in T, it's in T. Right? So that's your function. So any ring containing R is an R module as well. Here's an example that's a little bit more exotic, and I want to bring this up now because, by the way, how many of you take the alpha? Okay, so how many of you are playing? Well, also, I think that part of what I do in sports will probably help with the linear algebra part of that as well. And I bring that up now because this next example we're going to look at much more in depth later. So here's kind of a more cool example. Let F be a field, any field, and I think I'm the time. Oh no. Let V be a vector space over F. By the way, what we're going to learn about later is linear algebra. Easy. Can anybody describe to me what V has to look like? As a module, any vector space of a field is a direct sum of some number of columns of the field, period. Right? It could be big. This could be an uncountable direct sum of S. But if this is a finite dimensional vector space, this is always Fn, no matter what. All right? And we'll see why that's true later. But at this point, we have a field, we have a vector space, and T from B to B, a linear function. I am going to make V an FX module. Notice, of course, V is already an F module, right? Because it's a vector space. Yay. But actually, I'm going to make this a module of polynomial ring. Notice this is polynomials. Okay? It's no longer a field. Now, what I have to do is I have to define a scalar multiplication. Uh, Any ideas? No? So I've got to figure out some intelligent way, take some random polynomial and multiply it by this vector. This has got to barf out a vector in D. Any ideas how to do it?
Replace that harvest of space with top.
Put T into this polynomial, and what do you have? Now you have just some bigger linear transformation that takes V to V. And you can verify that this satisfies everything you want. So this is kind of a cool way that we took a fixed linear transformation over a vector space V and turned it into, turned V into an FX module. And believe it or not, that is the key that we're going to use to actually do canonical forms of polynomial or for matrices. Here's another example. Six. If R is a ring, then I'm gonna put up again there. This. You write some number of copies of R, could be infinite, could be any cardinality. And here's the way the scalar multiplication works. R times an element Ri. So a typical element of this is, I'm not even gonna call it a sequence, it's maybe an account. I'll call it net. Where most of these are zeros, or some, is just a new net. So you can build, given a ring, you can build very, very large polynomials. Okay. Here is one more example, and then I'll. Here. You bring one. Whenever I write that, that means you need to bring with one. I stole the carrot save the last time because it's such a long time. And actually, I'm gonna come back. Let me come back to 7. I just realized I need to do something first here. Let me give you the next definition. This will make more sense. How many of y'all remember what a linear transformation is? Right? I mean, these are, now in hindsight, you know, more mathematics, you look back and I'll say, oh, what is a linear transformation? Well, it's just an abelian group homomorphism that respects the scalar multiplication. This is what an R module homomorphism is going to be. So let me give you this definition. Let's let A and B be R modules. And F may be. Oh. we say that F is a left R module homomorphism. If I had these big left. I need to satisfy two conditions. Number one, F of X plus Y is F of X plus F of Y for all X, Y, and R. I'm sorry, in A. And this means nothing more than, hey, look, F is an abelian group homomorphism. That's it. And what's this respect I keep talking about? F of Rx is R F of X for all R. So this is exactly what a linear transformation is. Again, notice the left, the R is on the left. You can also do a right R module homomorphism. And in most of what I do will be commutative, so we don't even have to make that distinction. So this is basically a linear transformation. And in fact, if R is a division ring, we call this a linear transformation. So it's just an abelian group homomorphism that respects the scalar multiplications. Scalars can always factor out. Let's go back to example 7. That's how I told you this is. We're going to talk about this more extensively later, but we define hom, that just means homomorphisms. What is this graph anyway? This is the set of F from end to end, such that F is R module. Homomorphism. This is another example of an R module. I have taken its homomorphisms and turned it into a freaking line, right? How does this work? F1. How do I define the function F1 plus F2, if F1 and F2 are on R? Point lines. It's easy to see that this is an abelian group. It's associative because addition of functions is associative. See what else do I need? Certainly it's got the minus sign, right? Because the minus F just takes everything minus the opposite sign. What's the identity of this? What's the additive identity?
zero.
and everything's zero. That's the end of that. And not only that, home is an R module. Right? How does scalars work? Then well, it's just R and N, right? So my new function RF takes M to R times F of M. You should probably verify for yourself that this is in fact an R module, that home RMN is in fact an R module. Okay, any questions on that so far? Okay, this is a good point, I think, for me to talk about the homework, because I think I've given you all enough language to believe. Okay, so the first homework, some stuff about modules. Let's do a week from Friday. There we go. Again, you may assume that all modules are unitary here. The first one, let R be a commutative ring of identity in any R module. Show that as R modules, there is an isomorphism between home R, R to R, comma M to M. Right? Now, what is home R? I know what M is, it's just a bunch of M's. What is that home? These are all the homomorphisms that take the R module R, right? R is ring contains itself, so it's an R module. And it's actually a especially easy one. There is so a typical element is something whose input is R and its output is M. So see if you can think about how you can take a function from R to M and get something from M. And I'll give you a little teaser of a hint here. What makes this problem easier to deal with is the fact that R has an identity. It has a multiple identity. Okay. Number two is kind of getting a feel for how some of these modules work, and we're going to use some of these modules in the future. Suppose R is a commutative ring with one, M is an R module, and little m is an element of M. If you consider the set I sub M, which is all the stuff in R that kills M, right? R times M equals 0. Notice that IM has at least 0, and it doesn't, right? But it may have more stuff. Show that this is an ideal of R. And just kind of for your information, if that ideal is non-zero, then we say that M is a torsion element. Part B, if R is an integral domain, then show that the set of torsion elements of M forms a submodule. So if you collect all the torsion elements, as per the previous one, it forms a submodule of the module itself. It is very important in part B that R is a domain. Because actually I asked you, I mean, it is that if R is not a domain, it is possible sometimes for torsion elements to form a submodule, but not always. Give me an example where this fails. In 3, suppose that F from A to B is an R module homomorphism. Show that F is an isomorphism if and only if there's an R module homomorphism in the other direction that composes both directions to the identity function. Right? Don't beat number 3 to death, right? What does an isomorphism mean? It means that it's a homomorphism that's also one-to-one and onto, right? You should know from back in the day that anytime there is a function that's one-to-one and onto, then there's a function in the other direction such that these compositions hold, right? That's basically from a beginning proof, right? I agree. The tricky part is to show that G, that inverse function, is in fact still a homomorphism. That is the crux of the problem. It's not that there exists a G that inverts it to the identity. The thing, the important part is you build this uniquely and it still turns out to be a homomorphism. That's the part that's perhaps not clear. Number 4 is a kind of a fun puzzle. Suppose you have a homomorphism from A to A, an R module homomorphism, and suppose it's idempotent in the following sense. Suppose that f of x is f of x, right? So you take x, you do f, and it goes to f of x, and then you do f to that again, and it just stays there forever. Show that A is isomorphic to the kernel of this map for its independence. That's a thing. And finally, I do this last example to show how tenuous this can be. Q is a Z module. It's an ability group. We've already established that. It is impossible to make Z a Q module. And this will actually follow stuff very easily that we do later, but I think it's important to sit down and do the computation. It's not too difficult to show once you see what to do, but it is impossible to put a Q module structure on Z. And the only way you get, or it's impossible to put a unit to it. So that should be a lot of fun. Any questions so far? All right. Kind of the first real result outside of examples here. This one's not difficult to prove, and I'm sure you did something like this in 8510 for the analog kind of homomorphisms, but the from M to N, the R module homomorphism. B from M to N is an R module homomorphism if and only if the can be written this way for all X, Y, and N. Let me point out that if phi is an R module homomorphism, let me just sketch this. Then that's true. Everybody agree with that? Because both of these chunks, X and RY, are both elements of M. So I can break it up this way. And now I can slide that scalar out. And so there you go. That I think is the easier direction. How about the other direction? Draw R and R, X, Y, M, B, X plus RY is V of X. I need to show it's a homomorphism. One. Let R be one, right? I feel like I need a shower. That's kind of feel icky after doing that. Phi of x plus y is phi of x plus phi of y. Right, just think part one. And how do you suppose I'm gonna deal with the other one? They'll let x be zero. The only thing I really left out is phi of x must be zero, but again, remember, this is well, actually. Well, I assume that's not much. Well, let me be sure. If x equals zero, then I have phi of x y is. Oops. So far, right? But why does phi of x have to be zero? That's right. So. That's right. You take x and r to both be zero, then I have phi of zero, because after all, this is zero now, is phi of zero plus zero is phi of y.
Well, whoops. Line through, right?
Yes. Yeah.
Right.
Let's try that again. By taking x equals 1, that's going to be phi of y is phi of 0. Well, right. There we go. Now you cancel the phi of y's, because actually this all happens in the Boole group. Right. So I get phi of R y, which is exactly what. Very good. Okay, any questions? Questions on that? All right, well, you all have a good one. Let me know if there's any questions, and other than that, I will see you on Friday.